Here volume is
No,
very less. It's not
no,
audible.
okay, we are able to hear you. Do we have the CV of the speaker?
Adithan,
Yes, sir. Yes, sir. Actually, sir asking CV.
can you increase the volume? Meeting volume.
Can I increase the volume? Is it possible? Is it possible, Adithan?
Illa, sir.
Yes. Sir, increase volume is actually, sir, Bapuji, sir. உங்க சிஸ்டமோட வால்யூம் மட்டும் இன்க்ரீஸ் பண்ணி பாருங்க. என்ன கேக்குதா அவருக்குன்னு பார்க்கலாம்.
இல்ல
அவங்க மைக் ப்ராப்ளம்.
அவங்களுக்கு தான் சார். அப்போ
கேக்குது சார். கேக்குது அவர்
பேச. You are audible Sasikumar.
Sasikumar சார், நாங்க பேசுறது கேக்குதா?
Yes sir, your volume is very low.
Your voice is clear sir.
அது உங்க சிஸ்டத்துல தான் அந்த மாதிரி கேக்குது.
Sasikumar sir, your voice is clear.
Sasikumar, use headphone. Then you may hear clearly.
You can use headphone, yeah, better.
No, I am in headphone only.
Okay. No, we are able to hear your voice. We are able to hear your voice, no problem. Bapuji?
Yes, sir.
All the technical things are okay?
Okay, sir.
From your side?
Yes, sir.
So you can record suitably.
Started, sir. Started.
From the beginning of the program?
Yes, sir.
Have your eye on all the participants, okay?
Yes, sir.
Okay then. So shall we start?
Yes.
Okay then. Good morning to one and all present here in the e-meeting. I welcome you all for this 7th day of the faculty development program that is being organized in our department through Zoom platform. Due to the pandemic situation, all the universities and colleges are closed. Our management has requested us to conduct a faculty development program for the benefit of our own faculty members. Also, one more program for the research scholars during this pandemic situation. As per the request, we have planned 2 programs. One is faculty development program that is being conducted from 6th July to 16th of July for the benefit of our own staff members from other departments of KTR campus, staff members of other department in Vadapani campus, Ramapuram campus, and Modulus campus. The purpose of conducting this program is to make the faculty members aware of the speaker's point of view and the latest techniques developed in the field of mathematics, and to revise the basic concepts, to give an exposure for online teaching, so that in the next semester they can do better online teaching. So I welcome the speaker, Dr. Lakshmanan, who is going to give a talk on is going to give the talk on non-linear dynamics in an evolution science. I welcome the professor for accepting, for delivering the lecture. Also, I am very thankful to you, sir, for accepting our invitation in short notice. I also welcome faculty members belonging to our own department, faculty members belonging to other campus, and the faculty members belonging to other departments for this EFDP. Our plan is to conduct a research development program for the benefit of research scholars during 17th of July to 28th of July. I hope the program is useful to you, and we are also getting good number of participants during all the days. Today is day 7, and today we have our speaker, Prof. Lakshmanan, who is waiting here to give his lecture. I request Professor to share your view about online teaching. Also share your experience, how your university is planning for online teaching, and whatever experience you have about online teaching to our faculty members, so that it will be very useful for our faculty members. I request Professor Sasikumar to introduce the speaker to the audience. Sasikumar, please.
Good morning to all of you. This is Sasikumar from Department of Mathematics. I'm going to introduce the speaker part of today's talk. Professor Lakshmanan, Professor of Eminence and DST-SERB, distinguished Professor Bharathidasan,
Shashikumar, little bit louder. Little bit louder.
And topic for today's talk is nonlinear dynamics and evolving science. Today's talk is going to be given by Dr. M. Lakshmanan, Professor of Eminence and DST-SERB Distinguished Fellow, Bharathidasan University. So I give a brief introduction of the professor. Professor Lakshmanan specializes in the area of nonlinear dynamics, theoretical physics, with special reference to solitons, nonlinear evolution equations, and chaos. He made very in-depth contributions to the general theory of solitons, integrable systems, magnetic and optical solitons, classical chaos, including bifurcation, controlling, synchronization, and secure communications, as well as quantum chaos and spatio-temporal patterns. Professor Lakshmanan has written over 350 research articles in international reputed scientific journals and published 8 books through reputed publishers in the area of nonlinear dynamics, theoretical physics. He has about 40 years of teaching and research experience and guided over 32 students for PhD degrees. He currently is supervising 4 PhD students and several postdoctoral fellows. He has received some highest awards in India, including S.S. Bhatnagar Prize in Physical Sciences in the year 1989, UGC Hariom Trust Convenor Saha Award in Theoretical Sciences in the year 1990, Tamil Nadu Scientist Award in the year 1994, Viren Roy Memorial Lecture Award of Indian National Science Academy in the year 1998, 76th Indian Science Congress, Madurai Kamaraj University Distinguished Scientist Award in the year 2004, Royal Prize in Physics in the year 2005, Professor V.V. Arlikar Memorial Lecture Award, INSA, in the year 2006, R.D. Birla Award of Indian Physical Society in the year 2014, Shastra G.N. Ramachandran Award in Physics in the year 2019, and recently DST-SERB Distinguished Fellowship. He also awarded DAE Raja Ramana Fellowship, DST Ramana Fellowship, INSA Senior Scientist Award, and NASA Nazi Platinum Jubilee Senior Scientist Fellowship at different periods. He has been a recipient of several prestigious international fellowships, including Alexander von Humboldt Foundation Fellowship, Germany, year 1982, Eindhoven University Postdoctoral Fellowship, Holland, 1978, Swedish Guest Research Fellowship in the year 1981 and in the year 2000, Japan Society of Promotion of Science Fellowship during the years 1984, 85, 2002, and 2006, ICTP Senior Associateship during the year 2002 to 2008. He is also a member of editorial boards of several prestigious theoretical physics journals, including Proceedings of the Royal Society of London. Professor Lakshmanan has been recently honored with the DSc honoris causa by University of Budva for his deep contributions to nonlinear dynamics. Professor Lakshmanan is a fellow of all the 3 academies of Science of India and is an elected foreign member of the Royal Academy of Sciences, Uppsala, Sweden. He is also an elected fellow of Academy of Sciences of Developing Countries, FTWAs. That was 2009. He has held visiting positions in many prestigious institutions all around the world, including countries like Bulgaria, Canada, China, France, Finland, Germany, Greece, Holland, Italy, Japan, Poland, Spain, Soviet Union, Ukraine, UK, and United States of America. Professor completed BSc Physics at NGM College, Pullepu, and MSc Physics, Madras Christian College. He obtained his PhD in 1974. The work was carried out in the Department of Theoretical Physics, then University of Madras, under the supervision of Professor P.M. Matthews, leading to research career in nonlinear dynamics. Then, after 2 years, completed postdoctoral research in Germany and Holland. Joined as the reader in physics at the Autonomous Postgraduate Center of University of Madras in the year 1978, which became Bharathidasan University in the year 1980. He was promoted as Professor of Physics in the year 1984 and became head of the department in the year 1994 up to the year 2006, and head of the Center of Nonlinear Dynamics during the period 1992 to 2006. And now he is working as Professor of Eminence and DST-SERB Distinguished Fellow at Bharathidasan University. I welcome Professor Lakshmanan. Passing over to the host.
Thank you, Sasi Kumar, for giving very nice introduction about the speaker. Whenever you deal with nonlinear dynamics, professor name is very crucial. We cannot omit his name. You have to see his publications. You have to refer his publications, and only you will get an idea about nonlinear dynamics and its latest development. So, such a great personality is waiting with us to deliver a lecture. Professor, I request you to start your lecture. Yes, sir. Professor, please.
Thank you very much, Dr. Bapuji and Dr. Sasi Kumar for a nice introduction. And I thank Professor Goindarajan for inviting me to this faculty development program. It's a great pleasure for me to address the faculty members and scholars and other people. So I will start sharing my screen. So so is my slide visible? Hello?
Yes, sir. Yes, sir.
Now I will enlarge my transparency. It will take a minute. Please wait. So I will be basically giving an introduction to nonlinear dynamics and point out some of the exciting recent developments if I have enough time in this next 2 hours. So I will start discussing about nonlinear dynamics and evolving science in this online program. So for both research and teaching in these difficult times of COVID-19, so we have essentially have to make use of this tool of online program. It's, I mean, without online program, we cannot progress much under the given circumstances, which is being followed widely throughout the world. Bharathidasan University is also organizing many such programs through their through Bharathidasan University Entrepreneurship Hub. So they are organizing many such lecture series, both for students and faculties and research scholars and so on. So you can visit Bharathidasan University website and get some idea of the kind of online programs that are available. But now I will start with my lectures with the basic motivation to point out that non-linearity is ubiquitous and it's all pervading in the physical world. So I will briefly explain some of the recent developments on the notions of integrability, bifurcations, chaos, synchronization, complexity, collective behavior, and so on, which are all interdisciplinary, but requires basically mathematics, as I will point out. We essentially deal with differential equations, and for mathematicians, I suppose it's one of the basic tools. But not only differential equations, but all aspects of mathematics are needed. At least I will indicate some of the possibilities. And so my lecture will start from some basic notions, and I hope to at least point out some of the recent exciting developments in the context of contributions from my own group. So let me start with my talk. This is the basic plan. Starting from an introduction, I will give some ideas on the basic ideas of nonlinear dynamics, why nonlinear dynamics is needed, what is the necessity, what is the difference between linear dynamics and nonlinear dynamics, and so on. In the context of, to start with nonlinear oscillators, I will start with simple oscillators, but then I will point out the dynamics, the study, the underlying mathematics is quite complicated, even the simplest systems. And then I will point out what happens when you consider coupled arrays, coupled dynamical systems, and so on. In this connection, I will introduce the notions of bifurcations and chaos. And then I will point out from another point of view, you can also identify coherent structures, solitons, integrable dynamical systems, besides chaotic structures. So I will spend a considerable time on these notions of solitons also. Then I will, if I have time, so I will briefly point out the notions of synchronization, collective dynamical states, and possible applications. So this will be my broad plan. So let me start with nonlinearity. What is nonlinearity? Why I want to consider nonlinearity? What is the consequence? When you look at, after all, science and mathematics, everything is basically is to describe nature. We want to understand nature, how it evolves as a function of time. But one basic characteristic, if you look around our nature, is that things change. In nature, everything changes. Nothing is permanent. Animals are born, they grow and die. So do plants. Planets move around, chemicals interact, crystals grow, water on the surface of the pond changes its course. Water in the river flows and so on and so forth. So everything changes, nothing is permanent. Change alone is unchanging. Matram என்பதே மாறாத ஒன்று, as Lord Krishna tells to Arjuna. And it was Isaac Newton during the 16th century who realized this from a scientific point of view, and he enunciated the three basic laws of physics which we study in school days. So Newton's law represents the changes. And in particular, the second law, the rate of change of momentum. Already Newton talks about change, rate of change of momentum, position and momentum. So they are the state representations. The rate of change of momentum is directly proportional to the force acting on the system. The force is the cause, and the change in the state is the effect. And Newton, simultaneously with Gottfried Leibniz, identified developed differential calculus to explain the consequences of his three laws in the form of equations of motion. So you can represent any physical system, however big or small, by making the observations at an appropriate distance. You can treat any physical system as a particle. A particle is a mass point, has no dimensions, but still you can attribute necessary physical concepts like mass, charge, angular momentum, and so on and so forth. So you observe sitting at the origin of a fixed coordinate system, Cartesian coordinate system, for example. When you observe the state of this physical system, like you draw a position vector. A position, I don't know whether you see my board, just a coordinate x, y, z, and you have a position vector r of t to represent this mass point with mass m, which I call as p. So a position vector r at a given instant of time, initial instant t naught. And then a force acts on the system. Because of that, this particle moves and follows a trajectory. So at an arbitrary instant of time, there's an arbitrary vector r of t. So the position vector r of t. Once you have the position vector, you can define the velocity vector v, which is nothing but dr by dt. Position vector, the velocity vector is dr by dt. The position vector is r. And so you can define a momentum, mass into velocity, m into v, which is nothing but m dr by dt. So that the second law becomes without loss of generality. Rate of change of momentum, dq by dt equal to f, vector f, p is a vector. So you have, but p is nothing but m into dr by dt, and if you treat m as a constant, which is not always true, but for example, rising of a rocket, mass can change, but in most situations, mass remains constant, so you can take it outside. So you have md square r by dt square equal to f, the vector f, which could be a function of position and the velocity and the independent variable time. So you have now the independent variable, which is the time. The time evolves independent of us, independent of anybody. So it's obviously an independent variable. And position and velocity, they are all dependent variables. So you have essentially a differential equation to describe the development of, the physical development of this particular system. It could be a pendulum, it could be a Kepler particle, a planet moving around the sun, a spinning top, or any other physical system, or a fly, or an atom, or anything. You treat this particular system as a single particle. So you have a defining equation, a mathematical equation, a second order vector differential equation. Md square r by dt square equal to f. So given the form of the force, it could be, for example, inverse square force for a planet moving around the sun, or it could be the Hooke's law for a pendulum, simple pendulum. F is proportional to, directly proportional to the displacement, and so on. So this is a mathematical differential equation. So for example, if we want to describe the pendulum, you give the appropriate force, then you have the description of the pendulum. But that is just a mathematical description. You could have thousands of pendulums in this world. I want to describe a particular pendulum in my laboratory and so on. So how do you ascribe this particular system? You associate, you make observations at an appropriate instant of time, which I take the initial instant, I call that as 0. So you make observations, experimental observations. The position and the velocity r dot is nothing but dr by dt at t equal to 0. So these two variables define the state of the system, position and velocity, or position and momentum. So given this initial value, so you call this as initial value, then the problem of this particular physical system, particular pendulum or particular planet, etc., boils down to solving this differential equation, Newton's equation of motion, to find the position and so the velocity for all future time t greater than 0. So essentially, the physical problem is converted, physical evolution, how the system evolves in time is essentially converted into a Cauchy initial value problem for the second order differential equation. You can generalize this to an n particle system. For example, the 10 power 23 atoms in this room, in this hall. So you want to describe the dynamics of this 10 power 23 molecules. As a consequence, you can measure, you can concentrate on individual atoms, you can ascribe position vectors to each of these particles and the corresponding velocities and so on. You can do the force law, and then you can write down this 10 power 23 equations of motion. Or the entire solar system, for example, the sun and its 8 planets moving together. So you can ascribe position vectors to each of these entities. And then under inverse square law between all these planets, etc., you can ask how the general solar system moves. So you can also consider an n particle system, which means you have, for each of these particles, you have a second order differential equation described by the corresponding force acting on the system, which is not only a function of that particle, the ith particle, but it is also a function of all the position vectors and all the velocity vectors and then the time. So you have essentially a system of n coupled second order differential equations. And this you can associate with the physical system you want to investigate by assigning appropriate initial conditions. The position vector at the given instant of time, the origin of time at t equal to 0, Ri at t equal to 0, I running from 1 to n, and Ri dot, the velocity vectors of each of these particles. Then solve the Cauchy initial value problem subject to this initial condition. I solve in this system of n coupled second order vector differential equations to find the values of the position vectors of all these particles at any future instant of time t greater than 0 and Ri dot t. Then you are able to follow the entire evolution of this n particle system for all future instant of. So Newton's equations in principle tells you how to describe the evolution of any future system. And physicists and mathematicians towards the end of 18th century started believing that everything is known about the world, in this world, however complicated it is. Because you have to essentially solve the Newton's equation of motion, however complicated it is. If you are unable to solve today, tomorrow somebody will come, or somebody will invent a supercomputer. You will be able to solve the thing. So there's nothing unusual that remains. So as Laplace, Simon de Laplace, all of you know, Laplace transform, the French mathematical physicist, claimed that for a super intelligent person, future is as clear as the past. By which he meant, given the initial conditions, give me the force of all the particles acting on all the particles in the universe and the initial state, then I will be able to predict the future as accurately as possible, as required. This is called Laplace dictum. So to believe that everything is known about science and nothing more to be known. But of course, we know that there are lots of limitations. So when I say n particle system, 10 power 23 or more, n is essentially going to infinite, very large number of particles. You have to solve very large number of coupled second order differential equations. Though in principle it may be possible, but in practice it's quite difficult. And moreover, if we want to consider the dynamics of this room, etc., we are not interested in the individual motion of each of these atoms or molecules. What we are interested is in the average property, average energy, for example, temperature, the volume, the pressure, and so on. some thermodynamic quantity, some average quantity. So you can try to develop an average mechanics or a statistical mechanics. So people have developed statistical mechanics to describe such average properties when you have very large number of physical systems. They also say, given the initial conditions, position and velocity at an appropriate time, say initial time, t equal to 0, under the impression that I can measure these things as accurately as I want, with infinite accuracy perhaps. That's what is assumed when you say that the Newton's equation of motion correctly prescribes the evolution of this entire physical system, n-particle physical system. But is it always true? No. When you go to smaller and smaller scales, atomic scales, subatomic scales, you have to measure the position and velocity or position and momentum simultaneously with infinite accuracy. But as you know that in the beginning of the 20th century, it was shown and Heisenberg postulated that there is an intrinsic unpredictability, so-called uncertainty that's coming into picture in the measurement process. So there will be always this intrinsic unpredictability. You have to incorporate the Heisenberg uncertainty relation into this Newton's description. So you have to modify the Newtonian mechanics in the form of what is known as quantum mechanics to describe the evolution of the dynamics of particles under extremely small scales, atomic, subatomic scales, and so on. So you require a different description, probabilistic description, and so on. Intrinsic uncertainty you have to incorporate. So that is again a further limitation on Newtonian description. Then there was also another limitation. It says, given the initial position, yes, the particle can live anywhere in this three-dimensional world, the infinite world. So Ri can take any value, unbounded. But what about velocity? Newtonian description, there is no limit on the velocity with which a particle can move. But again, in the beginning of 20th century, Albert Einstein came and he postulated that no material particle can reach the velocity of light. Light alone can travel with velocity of light, that is c equal to 3 × 10⁸ meters per second. No other material particle can reach the velocity. So there is a limitation, there is an upper bound on the velocity. So again, in that case, you have to modify by relativistic mechanics. Leaving aside all these aspects, it has been identified during the past 4 decades or so. The form of this force, I have not talked about what is the nature of the force in this equation. The form of the force can also be associated with the nature of the differential equation, underlying differential equation. Whether the force is linear or not linear. What is linearity? The force has one-to-one correspondence with the dependent variables, which means position and velocity, not the independent variable. The dependent variable, the relationship between force and this dependent variable is one-to-one, linear, then it's linear. If it is not, it's non-linear. Why should one bother about such a, why should one distinguish with such forces? Because you have essentially, in the case of linear force, you have linear differential equations. And in the case of non-linear force, you have non-linear differential equations. And of course, as mathematicians, you know how difficult it is to solve non-linear differential equations. Linear differential equations themselves, under appropriate circumstances, they may pose lots of difficulties. But nonlinear, once you enter the regime of nonlinearity, things become extremely difficult. I may say each equation is a class by itself in general. So analysis of such nonlinear differential equations. For differential equations, you can consider difference equations or maps or integral equations, integral differential equations, partial differential equations. So everything, the same statement will hold. So distinction between the form in the form of the force, whether it's linear or non-linear with respect to the dependent variables, which are position and velocity, will distinguish the nature of the underlying dynamics. So I'll point out why one should consider such linear or non-linear force and what distinction it can make. So let me start with the simplest of the example. Just a simple pendulum under small oscillations, which everybody does in the school days experiment. So you have essentially force, a restoring force, F equal to minus Kx. K is the force constant. So you can essentially immediately write down the equation of motion. So you have in the case of the one particle system, so vector R, it has just one component X. So normally it has X of t, Y of t, Z of t. Y of t, Z of t are 0, so you have just X of t. So you have this vector differential equation, second order equation, reduces to scalar second order differential equation. M d square x by dt square equal to F. F is a scalar, F equal to minus Kx. So essentially then you have the equation reducing to M d square x by dt square plus Kx equal to 0, which I have rewritten as x double dot plus omega naught square x. Omega naught is nothing but square root of k by m, and dot is nothing but d by dt plus derivative. So this is just shorthand notation, which is used. Anyhow, so this is the simple differential equation, d square x by dt square plus omega naught square x equal to 0. So this is a second order constant coefficient differential equation. And it is a linear differential equation. Why it's a linear differential equation? Because the force is directly proportional to x, the dependent variable, and its properties, more importantly, its properties tells that this equation is a linear differential equation, to which I will come. Of course, you can, how to solve this simple differential equation. You can solve it subject to the initial condition. For example, an obvious initial condition, I pull the pendulum apart and allow it to oscillate. So what could be an obvious interesting physical condition, initial condition? So at t equal to 0, it's maximum amplitude, and I'm at the point of release, and at the point of release the velocity is 0. So x of 0 equal to maximum A, capital A, I call that as capital A, and x dot is 0. So the solution subject to this initial condition is x of t equal to a cos omega naught t. So this is the solution of the initial value problem. X of t equal to a cos omega naught t. So I can figuratively, schematically represent this solution either as a time series plot. Means how this dependent variable, and you can also write down for the corresponding derivative. So x of t as a function of t. So time development is called time series. So what is the nature of the function? Obviously, it's a periodic function, period to pi by omega naught. So it's a repeating periodic function. You can also equivalently represent this in the phase plane. X dot, x dx by dt, or m dx by dt, or mb plane, or xp plane, on concept phase plane. So x, you can write down x dot, which is just minus omega naught a sin omega naught t. You plot that, you'll find that will be a closed orbit, a closed trajectory. The phase orbit is a closed trajectory. Now you change a to some other value, a plus delta a, then you will find this curve will be again 2 pi periodic, and here again it will be a closed curve. So a series of concentric curves. But now let me introduce a nonlinear force, okay, which is a stronger force, minus kx minus lambda x cube with the nonlinearity parameter lambda. So what is the corresponding differential equation? It is mx double dot plus kx plus lambda x cube etc. equal to 0, which I divide by m, so I can rewrite this as x double dot plus omega naught square x plus lambda x cube equal to 0. Now you can also solve this equation. Then this requires introduction of new kinds of functions, namely elliptic functions. I'm sure as mathematicians, all of you know, elliptic functions are doubly periodic functions, one real period, one complex period in general. And in particular, this differential equation you can rewrite in terms of the so-called Cn elliptic function. So, you know, there are three types of elliptic functions, Cn, Sn, Gn. And these elliptic functions are characterized by the so-called modulus parameter. And this modulus parameter, k square, modulus square. And this k square can vary from 0 to 1 in general. So when this modulus k square is 0, Cn becomes cos, which corresponds to lambda equal to 0, no unharmonic force. It's only linear harmonic oscillator, which we just now saw. It is it's a cos omega naught t. And the corresponding frequency you find. So the general solution of this nonlinear oscillator equation is unharmonic oscillator is x of t equal to AC and omega t, subject to the initial condition at t equal to 0, x of 0 is capital A and x dot is 0. Then this is the solution, Cn omega t, capital omega t. But this capital omega is square root of omega naught square plus lambda a square, where lambda is the nonlinearity parameter. And observe the most important thing, that this initial amplitude, initial value or initial condition also appears inside this frequency parameter. So the qualitative property of this solution also depends on the initial value. The larger the amplitude, the larger the frequency, and so on. So already you see an important distinction between linear and nonlinear differential equations. Most equations will show a dependence on the initial state. And this dependence can become very crucial. It can be very sensitively dependent on this initial condition, which we will soon see. And associated with that, as I said, there is a modulus parameter, and this modulus parameter, in this case, lambda a square by 2 omega naught square plus lambda a square, so it varies from 0 to half. Maximum value when a is infinite, so this takes the value half. But there will be, for example, if omega naught square, if the sign in front of this omega naught square is minus, there will be a minus sign here, in which case it can take the value 1. In which case, this Cn function will become hyperbolic function, secant h. So when k, the modulus parameter, varies from 0 to 1, this function Cn varies from cos to secant h. The secant h function will play a very crucial role in nonlinear dynamics, particularly in solitons and so on. We'll come to that. So this is the property of Cn function. Similarly, Sn, that will vary from sine and tan.
Sir, one doubt, sir. Sir, one doubt, sir.
Sure.
Sir, here you assume x equal to a Cn omega t and then trying to find the value of omega and k, or?
I have not assumed. I have deduced. I have solved the initial value problem. You can solve this equation and you obtain AC and omega t. And you will find omega, capital omega, will be square root of omega naught square plus lambda square. This is the exact solution, most general solution of the initial value problem.
Okay.
So if you have a Sn function, that will vary from, change from sine to tan h function. Similarly, Dn function will vary from 1 to secant h as k varies from 0 to 1. So these are the so-called
initial conditions are same. Initial conditions are same. X of 0. What about the initial conditions? X of 0 equal to 0, x dash of 0 equal to 1. You assumed the initial conditions?
No, I have assumed the initial condition as in the previous harmonic oscillator. Yes.
Okay, okay, same
Except
conditions.
you pull the pendulum apart or you pull the oscillator apart, the maximum amplitude is A at the time of release.
Okay,
Capital A. And at the time of release, X dot is 0. So,
got it.
just like cos omega naught t, you can calculate X dot of t. Sorry. So you can calculate X dot of t, that will be minus capital omega A Sn omega t dn omega t. So at t equal to 0, that will become 0. And X of 0 is A Cn0, Cn0 is 1. So it will be X of 0 is 1. So that satisfies the initial condition correctly. That is the standard property of
Okay,
the harmonic. So you should try to, as mathematicians, I mean, it's a simple nonlinear, not simple, but it is the basic nonlinear differential equation. How to solve this differential equation, how this function can be defined, how this modulus parameter can be introduced, and so on. So that will be a good, good lesson to learn about nonlinear differential. So I urge all the students to see how this equation can be solved. Even though it's nonlinear, you are lucky to solve this by introducing this new kind of function as Jacobi had done. You have also other possible functions, Weierstrass function, equivalent function, which is more complicated notation and so on. And Cn function, Sn, etc. are related to Weierstrass function rho. Similarly, you have theta function, etc. So there are 3 possible descriptions of this elliptic function. But I like this Jacobian elliptic function, simple to describe. It has direct contact association with harmonic and hyperbolic function. So what is the distinction then you can identify between the linear harmonic oscillators and non-linear harmonic oscillator with the reference to these 2 examples? For the linear harmonic oscillator, which is associated with the linear, I call as linear differential equation, because if x1 is a solution to that differential equation, x double dot plus omega naught square x, and if x2 is another independent solution, linearly independent solution. You know, there are 2 linearly independent solutions. What are they? X equal to cos omega naught t. X equal to, next one, sin omega naught t. They are not linearly dependent because sin square omega naught, sin omega naught t is square root of 1 minus cos square omega naught t and vice versa. So they are not directly proportional. They are non-linearly related. So they are linearly independent functions. Now, these 2 are independent solutions. Their linear sum is also a solution. x1 is cos omega naught t, x2 is sin omega naught t, and the linear combination where a and b are arbitrary coefficients. In general, they could be even complex. So a and b are arbitrary constants, a cos omega naught t plus b sin omega naught t. That is also a solution. You can just substitute and check. You can rewrite that as capital A cos omega naught t plus delta. Or if you expand cos omega naught t plus delta, then you can see what is, how is A related to A, small a and small b. So this is the most general solution. Now the initial value problem, I said at t equal to 0, x of 0 is capital A, so delta will be 0. So correspondingly, x dot will be 0 at t equal to 0. So initial value problem also comes. So the important property of this linear differential equation, which is also true for any other linear differential equation, homogeneous linear differential equation, is that it will admit, if it is an nth order differential equation, it will admit n linearly independent solutions. And their linear combinations will also be a general, and will form the general solution, most general solution. But what about the anharmonic oscillator, which I pointed out? I said x1 equal to cn omega t is a solution. Now take any other solution and ask the question, same question, whether you can have a solution ax1 plus bx2 as a general solution. you'll find it will never be a solution unless A and B are simultaneously zero. Small constants A and B are simultaneously zero. Because if you substitute this solution into this differential equation, each one, x1 has to satisfy this cubic equation, x2 has to satisfy this cubic equation. Substitute that, then you'll find the sum terms are remaining. So this will never be zero unless you put those combination coefficients zero. So finally, for nonlinear systems, linear superposition principle fails. So that is the most important aspect you learn even from these two simple examples. So this is true for any nonlinear system, linear superposition. That would be nonlinear superposition. I'm talking only about linear superposition. Linear superposition principle is valid only for linear differential equation. Take any differential equation for which linear superposition principle fails, then it's not a linear differential equation, it's a nonlinear differential equation. You can check for any such differential equations. Now, what is the consequence of this? Now, all the techniques and methods normally you learn, the Fourier transform, the Laplace transform, the Green's function techniques, the various spectral techniques, etc., which has been developed over the past 300 years, and so on, are valid, are based on this linear superposition principle, Fourier series, Laplace integral, etc. Everything is based on this linear superposition principle. And if this linear superposition principle fails, then the general methods, general methods which you have developed for linear differential equations will not work for nonlinear differential equations. As a consequence, you find each equation requires an independent analysis. And you may encounter, even with very simple nonlinear differential equations problem, you may not be able to solve the simplest of differential equations, though you have succeeded to solve the previous unharmonic oscillator equation by defining new function, but this is not always possible, as I found out. So this is where the development of nonlinear dynamics starts. That the realization that when you take a nonlinear dynamical system, the linear superposition principle fails. And so new methods and techniques have to be developed. As a consequence, you find new behaviors. Solutions may take new properties. And so the corresponding physical systems can exhibit novel structures. This is what I will point out. Very quickly, I will go back to linear differential equation, the damped harmonic oscillator equation. So you have the damping force, x double dot alpha x dot. X dot means dx by dt. So this is a friction term. And you know how to solve these equations. The method of indices, indicial equations, and then you look for solutions of the form e power at, something like that. Then you find the possible roots, indicial equations for that. So you have in this equation, you have subcritical, supercritical, and etc. So you have three possible situations. So for this subcritical value, you find that this because of the damping. So what I have shown the solution, you know the exact solution. It will be again an oscillatory solution, oscillatory function, but multiplied by an exponentially falling function e power minus alpha t or something like that. So you can write down the exact solution, but I have shown it pictorially. So in the x dot plane. So what happens? You start from somewhere from the initial state, anywhere in the x dot plane. Then you start integrating. The system keeps on amplitude keeps on decreasing because of the damping, and finally it settles down at the equilibrium state, which is the origin, x equal to 0, x dot equal to 0, for the underdamped case. So underdamped, overdamped, critically damped case. These are critically damped cases. Okay. Now, so that's all trivially known, you know the solution, etc. But you see the plot, And wherever you start, it approaches in the underdamped case towards the equilibrium point. Now I ask the question, suppose I start from a different initial condition, which could be even far away from the original initial state. And I ask how this system will evolve asymptotically as t goes to, it takes very large values. You find, again, the system approaches, and finally it settles down to the same equilibrium point, the fixed point. So even if there is large changes in the initial condition, the ultimate evolution, there is not much change. So that is another important property you will observe for the case of linear systems. Initial condition doesn't matter much in general. Now I take a slightly more general equation. A forced damped harmonic oscillator, for example, a forced LCR electronic circuit. So current or voltage, for example. So you have damped oscillator, then you are applying impressed external forcing with the impressed frequency omega, which is different from, there is a mistake, it's omega naught square, not omega naught. Omega naught square x equal to f sine omega t. So this omega impressed frequency is different in general, different from this system frequency omega naught, natural frequency. So you allow the system being, you're supplying energy from outside in a periodic manner. So what is the nature of this system? Again, you can solve this. The linear inhomogeneous equation. You know how to solve this. The solution is solution of the homogeneous part plus a particular integral, which is solution of the entire equation. The homogeneous part, anyhow, because of the damping, will die down, but the inhomogeneous, the particular integral, will have a form which allows resonant oscillation, resonant periodic oscillation with frequency 2 pi by omega, frequency omega by 2 pi. So this is what happens. I start from some initial condition. This is xx dot plane. This is the time trajectory, x versus t. You can solve the, find the exact solution, but it's sufficient if you concentrate on the picture and the schematic representation. You start from some arbitrary initial condition inside a circle of certain length. Then you find as time develops, it oscillates periodically with period equal to this external forcing frequency. But then ultimately it settles at a fixed amplitude of oscillation. A limiting periodic oscillation, a limit cycle oscillation. So this is a limit cycle. Similarly, if you start somewhere from outside this limit cycle, again you will end up, it will start spiraling and then end up in this limit cycle asymptotically for large values of t. So the system starts resonating with the external forcing frequency. Again, if you see that the different initial conditions ultimately leads to the same final state, periodic state, the limiting periodic oscillation, namely the limit cycle oscillation. This is the nature of the dynamics of linear oscillators, damped oscillators, forced oscillators. Now I ask the question, if I introduce non-linearity as in the case of the unharmonic oscillator, simple non-linearity, and forcing and damping, what happens? Then you see the full force of non-linearity. We have already seen the unharmonic oscillator. There I called the unharmonicity parameters lambda, but here I have changed it beta. There's no specific reason, but just for convenience. Okay? X double dot plus omega naught square x plus beta x cube equals 0. Again, you have this CN solution. Omega bar is nothing but omega naught square plus beta s square. So you have oscillation. And if you change the initial condition, you have concentric curves, even with this elliptic function. And add damping, again, you have damped periodic motion for under damping and so on. But more interesting problem is the one which, the next case. The forced unharmonic oscillator, damped forced unharmonic oscillator. This is also called Duckling Oscillator. Duckling was a Dutch physicist, electronic engineer, electrical engineer. He was studying the properties of triode and pentode valves in those days, in early 1940s, 50s, and so on. Current, voltage, etc. And you can show that the corresponding dynamical equations of this form. X double dot plus alpha, this damping parameter alpha, plus or minus omega naught square. I have included both plus and minus for some convenience. Plus beta x cubed, the non-linearity parameter, the external forcing F, the strength of external forcing is F, and the periodic function is sine omega t. So this is again the inhomogeneous term. This is a homogeneous equation, but non-linear because of this x cubed term. You would have already realized that a simple way to check whether a given equation is linear or non-linear, see whether after rationalization you have the dependent variable or the independent or its derivatives have degree different from 0 or 1. Okay. Here the degree is 3. Then it's a non-linear equation, non-linear differential equation. So you can check whether linear superposition principle is valid or not. If it's valid, it's a linear differential equation, a linear dynamical system. If it is not, it's a non-linear dynamical system. We can also check from the degree powers of the dependent variable and its derivatives, whether they have a degree different from 0 or 1. If it is 0, then it will correspond to this inhomogeneous term, and 1 that will be linear term. So different from 0 or 1, even fractions between 0 and 1, that will be non-linear equation. So this is a fully non-linear equation. Now we can consider plus omega naught square x, which is the Duckling oscillator, which I discussed earlier. Minus equation also you can discuss. Again, that as elliptic function solution. That we call as a double well problem. Single well is also okay, but double well is much more interesting for the point of view I'm going to discuss. Now, I state that this equation cannot be solved exactly, analytically. All the mathematics development during the past 3-4 centuries does not help you to find an analytic solution, analytic function, which satisfies this simple second order nonlinear differential equation, scalar differential equation. Of course, you can find approximation methods, the perturbation methods. You can treat, for example, the nonlinearity parameter as a perturbation, as a small perturbing force, beta x cubed. Beta is extremely small compared to the other parameters and so on. So you can try to develop a perturbation series, Lind's Poincare perturbation method, or many other perturbations. But the perturbation methods will have their own validity. And in fact, you can show that beta equal to 0, I mean, there is some essential singularity associated with this problem and so on. So the perturbation series is not a very natural representation, though it helps in some certain practical purpose. But in order to understand the full dynamics, you have to solve this equation in a most general sense. So the only recourse that is left to us is to do a numerical analysis, which cannot be perfect like finding an exact analytic solution, but that is the best we can do. So you can go for a Runge-Kutta fourth order numerical scheme or any other convenient numerical scheme. And then you have to check the convergence, etc. But standard method is you take Runge-Kutta fourth order method scheme, and then you try to analyze this equation. And when you have plus omega naught square, the only equilibrium point is the origin, 0, 0, x equal to 0, x dot equal to 0. But when you have the minus sign, you can have 3 equilibrium points. The origin 1, there is a left fixed point which is equal to omega naught square by beta, or square root of plus minus square root of omega naught square by beta plus omega naught square by beta on the right side. So there are 3 equilibrium points on the real x-axis. And when we start introducing damping with no forcing, then naturally the system will approach towards one of the fixed point. You choose the initial condition such that, for example, a convenient one, you can choose the other one also. So you start from a suitable initial value. You find the system will end up when there is the external forcing 0. I call as such the control parameter. There are 5 parameters in this problem. The damping strength of damping parameter, the natural frequency omega naught, the external, the nonlinear force parameter beta and harmonicity parameter, the strength of external forcing, and the period of the impressed frequency omega. So these are all external parameters. We can vary these parameters from outside, so that we can control them. So normally in dynamics language, you call them as control parameters. But you will see that there are 2 parameters you can scale away, because you can make a scaling of x and make a scaling of t. So essentially there will be 3 independent parameters. For example, I can treat the 3 parameters as beta, f, and omega, or alpha, beta, and f, or something like that. So in this problem, I will choose beta, f, and omega as the 3 independent parameters. Now, I fix the alpha and omega naught and ask the question, if I change f continuously, what happens to the dynamics? After fixing beta and omega also, I will come to the variation of beta and omega soon. If I fix beta, omega and change f alone, then for f equal to 0, as I said, it will go to the left fixed point, asymptotically. Now I increase f. What happens to the dynamics? And you know already, in the case of linear damped forced oscillation, the system exhibits a periodic motion with period t equal to 2 pi by omega. And when you increase f to small values, similar periodic motion will occur around this fixed point, left fixed point. You will find numerically, after integrating and then plotting the values, you will find a closed orbit. As I said in the beginning, phase plane corresponds to a periodic motion. So I call this as a period t, period 1 or period t, 1t periodic motion, a limit cycle oscillator. But then when you increase f smoothly further, every time you have to do numerical integration, but that's a difficulty. And the problem is you can increase f in finite values only. How accurately, how small change you make, so that is not going to ever end. So you can change f by 0.1, units of 0.1 or 0.01, 0.001. So this can go on. But in some discrete values I change. And then, for example, a typical example, f equal to 0.33, I get a closed circle. But then the surprise comes. When I increase f further, at f equal to 0.35, for example, I get you get 2 circles, and there is a, because this is projected on x-xt plane. This is actually, you can treat this as a 3-dimensional equation. X dot, and then omega t as another variable. So I am projecting to x dot plane, and you find that there are 2 closed curves, which means to come back to the same value, it takes twice the time that the oscillation took here. So the periodic oscillation with period t bifurcates. This loses stability, and in place of that, a new qualitative orbit emerges, which is period twice the period of the previous one. So this is period 2t oscillation. In place of period 1t oscillation, now I have period 2t oscillation for f equal to 0.35 and so on. Now I increase the f in further in small steps. Now I find out f equal to 0.357. It's a 4t periodic oscillation occurs. I increase further, then I get 8t periodic oscillation occurs. Then 16t, 2 power. So this is 2 power 0, that is 1t. This is 2 power 1, that is period 2. This is 2 power 2, that is period 4. Then 2 power 3, period 8. then 2 power 4. This is 2 power 2, period 4, 2 power 3, 8, 2 power 4, 16, then 2 power 5, 32, 64, and so on and so forth. And then at f equal to 0.365 or so, you have infinite period oscillation. But it's all bounded. I say it is, there are the period of oscillation is infinite. That means it almost never comes back to its original value. But still it's bounded. It's not a periodic motion. It's bounded periodic motion where you have the period becomes infinite, 2 power infinite. And beyond that, more and more complex motion. So all these things you can represent in terms of what is known as a bifurcation diagram. X versus F by concentrating on the maximum, say for example, the maximum value of the amplitude of oscillation. I will show it in a more clear picture. So X versus F. So you see, until F equal to 0.343 or something like that, 345 or something like that, you have period 1 oscillation because the maximum value has just 1 value. Then once you reach this value, suddenly there are 2 possible maximum values. So you have period 2t solution, then you have 4 possible solutions, period 4 solution, period 8 solution, period 16 solutions, which all occur in a very narrow range of the control parameter F. Then beyond that, you have infinite number of possible values. So that's the situation where you have complex chaotic motion, where the system dynamics becomes extremely sensitive to initial conditions. And this is what happens at this point when F is process these values, these critical values, F equal to 0.357 or something like that. Then in this range, then it can take infinite number of possible values. And at this, in this range, in the figure I have shown here and beyond that, then you have the system exhibiting sensitive dependence on initial conditions, extreme sensitivity to initial conditions. What does that mean? Let me integrate the Duckling oscillator, the cubic and harmonic oscillator, the double well, and external forcing, periodic forcing at a critical value of the forcing strength, where it exhibits that infinite aperiodic motion, bounded motion. So I start from an initial condition, which is somewhere here, and I mark the points in a blue line, blue color. So I trace the development of the time series, X versus T. So you see, it oscillates, but not periodically. It increases, it decreases, it increases, decreases, etc., etc. So a periodic motion. It goes on. After I have omitted even some initial transients and so on. This is asymptotic motion. Now I start from another initial condition, which is extremely close to the previous initial condition, even in the 5th decimal or 4th decimal or 5th decimal, etc., which is very close to the initial value, x of 0 and x dot of 0. I integrate. I mark those points by this pink color. Initially, you don't distinguish. You can't distinguish the blue and pink color. They follow each other up to some finite time value, t equal to 30 time units of 1. Then there is separation. These two trajectories separate out. Then again they join. Then again they separate slightly. Then if you wait for sufficiently long time, some 40 or 50 time units, you see the blue line and the pink line, they separate out, and the difference between the two values is as large as the system size itself. The system varies only between -1.5 to +1.5. We find the variation can be as large as the system size itself. But then the motion has to be bounded, so it again comes back, exhibits the periodic but bounded motion in its own way. So if you find the average distance deviation between these two time evolutions, you find there is an exponential deviation of these two nearby trajectories. And this exponential deviation of nearby trajectories will cause a sensitive dependence on initial condition, because even there is a very small difference in the initial state, then the final state will be extremely different. And this is what made the great mathematical physicist Henri Poincare in the beginning of 1900s, his famous treatise, his famous study on the dynamics of the three-body problem, solar system, sun and the earth. When you have a perturbation of a second planet, Jupiter, for example, sun and earth, you know, the problem can be exactly solved. The two-body problem can be by simple linear transformation. You can remove the motion of the center of mass, and so effectively you have one-body problem that's a non-linear problem, but still you can solve that and you get all the Kepler's laws. But when you introduce the complication of a second planet, perturbation of a second planet, the problem becomes extremely difficult. It is not solvable even today. And Henri Poincare came to the conclusion in analyzing this three-body problem. He pointed out that it may happen that small difference in the initial conditions produce very great ones in the final phenomenon. Small difference in the initial conditions, as in this example. You make small difference in the initial measurement, initial conditions. It can make very large difference in the final phenomenon. And as a consequence, so what is the consequence? A small error in the former will produce an enormous error in the latter. Consequence, prediction becomes impossible. Essentially because of non-linearity. There is no non-linearity, so no unpredictability. This is an intrinsic unpredictability that arises because of the presence of non-linearity. So this is what Henri Poincare pointed out in the beginning of 19th century, beginning of the 20th century. It was not appreciated very much at that time until this phenomena was also realized in mid-1960s by this MIT atmospheric physicist Edward Lorenz, who studied the weather dynamics, which all of you know is in the form of Navier-Stokes equation, etc. But as a very, very simple reduction of this complicated nonlinear partial differential equation, it reduced the problem to a system of three coupled first order nonlinear differential. Again, nonlinear. And he found exactly similar phenomena, bifurcations, chaos, and so on, and sensitive dependence on initial conditions, as in the case of Duckling Oscillator. As small a perturbation as a butterfly fluttering its wings somewhere in the Amazons can in a few days' time grow into a tornado in the state of Texas. Butterfly fluttering its wings somewhere in the Amazons. Amazons where? In South America. If the butterflies had not fluttered its wings, the weather would have developed in some way, maybe in a smooth way. Just because the butterfly fluttered their wings somewhere in the Amazons, the weather has changed so that it grows into a tornado, cyclone-like situation in the state of Texas in North America, the United States. It can grow. Just to highlight how small effects can lead to very large phenomena in the ultimate. So this is what basically chaos implies. Sensitive dependence on initial conditions. You can understand this phenomena even more generally by going to a simple map, a quadratic map, and working out. So instead of differential equation, you can study the same phenomena in terms of a map. So what is a map? So you have a function xn, a function which is a variable of x, where the time is not continuous, but it evolves discretely. Just like, for example, you look at the population of a city or a species and so on. You don't measure continuously the population of a country every instant of time, but for example, in a month or in a year or a week, etc. So you treat the problem in a discontinuous way, in a discrete way. So n runs from instead of t, x of t, I call as x of n as a variable. N varies from 0, 1, 2, etc. So once you know x of n, you can consider a function f. So you map this function xn on to the next interval, n plus 1 time interval, by the map f of xn. So this is an one-dimensional map. So you have an one-dimensional differential equation. If it's a linear differential equation, it's very trivial to solve. For example, x of n plus 1 equal to a of xn is quite easy to solve. So every time, starting from x naught, the initial instant, that is the initial value, then next instant x1 is given as ax naught. So next instant a square x naught. So for example, if a is less than 1, the system converges towards the origin quite fast and so on. So there is no surprise as long as you have linear difference equation. But you introduce a simple non-linearity instead of axn, you introduce axn minus axn square. So this is the so-called logistic map, logistic population dynamics can be described by such equations, differential equations, so discretization, differential equation. So you try to find again the periodic solution. Here periodic solution means x of n plus 1 equal to x of n, x of n plus 2 equal to xn, that's 2 periodic, x of n plus capital N equal to x of n, that is n capital N periodic and so on. So, but here the advantage of this kind of maths is that you can find at least few periodic solution exactly, analytically. For example, the equilibrium point, xn equal to xn plus 1 equal to x star. So that is a possible solution. So if you put xn equal to xn plus 1 equal to x star, you get a simple equation x star into again a linear equation. So you find there are two possible solutions. x1 star equal to 0, the equilibrium point, or x2 star equal to a minus 1 by a is a finite value. So you can look at this exact periodic solution and ask the question, to slightly perturb the system, what happens from its equilibrium value, what happens? So you can just check from this map what happens when you perturb from that fixed point solution. So you'll find that the stability of equilibrium point is nothing but this variation delta n plus 1 by delta n. Delta n is the variation from the fixed point x star. So xn minus x star is the variation. And so you ask the question, what happens at the next instance of time, delta n plus 1 by delta. You can easily check that is given by the first derivative at x star. So that is a into 1 minus x star. And you have two fixed points, 0 and a minus 1 by a, and from which you can find that this 0 equilibrium point is stable for a less than or equal to 1. And the fixed point a minus 1 by a is stable for a lying between 1 and 3. So at a equal to 1, this x star equal to 0 becomes unstable and this becomes stable. So bifurcation occurs. One solution loses stability, in place of it a new stable solution which remains stable until a equal to 1 to 3. So this you can keep on proceeding further. So for example, you can get a 2 periodic solution, 3 periodic solution. For example, you can find a period T solution, period 2 solution, and that turns out to be, so you start from x1 star and you go to x2 star, and from x2 star you go to x1 star. So this keeps on going and you can find their exact value. And again, you can find the stability as in the previous case, and you can find the condition, for example, delta n plus 1, 2 by delta n modulus when it is less than 1. So you find that f prime x1 star, f prime x2 star, the product should be less than 1 modulus. And for the logistic map, it will be stable between 3 and 1 plus root 3 root 6, which is 3.449. So you can proceed ad infinitum. So this is period 2 solution, period 2 power 2 solution. You will find there is no period 3 solution, no period 3, 4 solution. You will find period 4 solution, then period 8 solution, etc. So you can proceed, you can find the stability and the values at which bifurcation occurs turns out to be 3, the first period, that the equilibrium point 0 becomes, or the fixed point becomes unstable. Then the next one, period 4 solution becomes unstable at 3.44. Then next solution 3.55, etc. And it goes. You see that the progression of this bifurcation value, the range becomes narrower and narrower, and it goes in a geometric way. So the way in which this bifurcation, successive bifurcations occurs, approaches a universal value called Feigenbaum's universal value. So you can explain everything that has happened in the case of Duckling oscillator. For example, the period 1 solution, what does that mean? X versus N. So period 1 solution means the value remains exactly the same after leaving the initial transients. Now I ask the question, if I change the initial value given considerably much, one starts as dot, another one is circle. You'll find as time evolves, both of them coincide. So there is no sensitive dependence on initial condition. Whereas when you have chaotic motion, randomly distributed for A equal to 3.9, you see sensitive dependence on initial condition. This is how the distance between the two neighboring points change in an arbitrary way. It covers the entire system dynamics in an exponential way and so on. So sensitive dependence on initial conditions. So can be also easily realized by going to this kind of nonlinear maps. So I have given you two simple examples by which you can realize one of the important consequences of nonlinearity. Bifurcations and then complex motion, chaotic motion, which exhibits extreme sensitivity to initial conditions, leading to unpredictability of future behavior. As small as a butterfly fluttering its wings leads to, in the Amazons, leads in a finite time, in a few days' time, to a tornado in the state of Texas. Small errors can lead to very large errors in finite time. Prediction becomes impossible in these situations, but not for every nonlinearity. So that is the crux of the problem. Which dynamical system will exhibit sensitive dependence on initial conditions? Which system will exhibit complete regularity? How do you identify? Now, as mathematicians, you can also look at the nature of these differential equations in the complex plane of the independent variable. So you can look at the singularities exhibited by the solutions of these differential equations. In general, the solutions can exhibit fixed and movable singularities. The singularities could be poles, which we are all familiar, branch points, essential singularities, and so on. But they could be fixed or movable. Fixed, yes, you have many examples. Most of the orthogonal polynomials, for example, Hermite equation, Legendre equation, Laguerre equation, etc. The system, the equation itself exhibits some poles which are reflected in the form of the solutions. But let me consider a very simple equation, dw by dz, which in the case of dynamical system, I call as xt, dx by dt. From a differential equation point of view, I call it dw by dz, and you can extend into complex z plane. dw by dz plus w square such a trivial nonlinear differential equation. This is a nonlinear differential equation. The linear superposition principle fails because W is a solution. A into W is not again the solution, the same equation. And this equation has an exact solution, I mean, general solution. You can integrate this trivially. dW by W square equal to minus dz. You can integrate and you'll get Wz is 1 over z minus z naught. And what is z naught? Z naught is the integration constant, the arbitrary constant. You can extend it to the complex plane. So z naught can be placed anywhere in the complex plane, complex z plane. So it's not a fixed pole. It's a movable pole. Can take any arbitrary value. So this nonlinear differential equation shows that it can exhibit a movable pole. Similarly, dW by dz minus dW equal to 0. The solution Wz equal to log z minus z naught. It's a movable logarithmic branch point. dW by dz, W into log omega W square equal to 0. You have Wz exponential z minus z naught inverse, inside exponential. It's a movable essential singularity. On the other hand, z d square W by dz square minus W square equal to 0 is again a nonlinear differential equation. Or you can even take d square W by dz square minus W equal to 0. So for example, in this case, the solution is Wz equal to 2 by z. It's a fixed singularity at z equal to 0, but that is already there in the, you can see from the equation itself. You divide by z, so it shows a fixed singularity at z equal to 0. That is reflected in the solution itself. That is fixed singularity. But these are intrinsic singularities. Now you can ask the question, this was asked by French mathematicians during the beginning of 1900s. Paul Pullepu and his co-workers to consider a second order differential equation of arbitrary form and ask the question, which of those equations which are free from movable critical singularities? That means critical singularities, out of these singularities, poles, branch points, essential singularities. Branch points, essential singularities are called critical singularities. Poles are not. So the question was, consider the most general second order differential equations and ask the question, which of those equations admit only movable poles and not movable branch points, essential singularity? And Paul Pullepu and his co-workers came up with a remarkable result. You can see the details in the book of Innes, Ordinary Differential Equation, L.I. Innes. There exist 44 canonical forms of second order differential equations, nonlinear differential equations, which allow only movable poles as their solutions in the complex plane of the independent variable, which are solvable in terms of elementary functions, including elliptic functions. But there exists another second order differential equations which cannot be solved in terms of any known functions, which require new transcendental functions, and these are called 6 Pullepu transcendental equations. The forms of which are all you can find, for example, from my book. I will give the reference in detail, reference at the end. So those are the equations. Those are the only equations which can admit movable poles. All the other forms in the second order differential equation, they will exhibit movable critical points. It's a movable critical points. So you can ask the question, this Duckling oscillator, or there are many other such systems, pendulum equation and forcing and so on, the many Lorenz equations, etc., etc. They are all non-solvable, non-integrable. So what kind of critical points, movable critical points, what is the structure? And over the years, in the past 20, 30 years, many mathematicians, including from our group, we have studied such systems and shown they exhibit very complex structures. Still, many people study the underlying dynamics. But when you go to third order, fourth order, etc., the problems becomes more and more complex. You can extend this analysis to partial differential equations. There you'll have movable manifolds, singular manifolds, and the structure of these manifolds, etc. To study them is an extremely interesting point of view to look at. So that is as far as ordinary differential equation concerned, nonlinear ordinary differential equation concerned, and the possibility of chaos. But you can also ask the question in those finite order ordinary differential equations. After all, we saw the unharmonic oscillator equation integrable in terms of elliptic functions. Kepler problem is solvable. So what kind of problems are solvable, exactly solvable, and so on. So one way to look at is try to see whether the singularity structure exhibits only movable poles. So there are many such techniques have been developed in recent times to identify such integrable equations. And our groups also, we have in a series of 6 papers in Proceedings of Royal Society, we have given a systematic method to identify such integrable equations and so on. But I will go to a more interesting problem to consider the notion of solitons. I think I have talked for quite a long time, so perhaps people may have some doubts or questions they want to ask. If they want to ask, they can, I think I will give a break so they can ask me any related questions they would like to ask. In the lecture I have discussed so far. So any questions that you would like to ask at this point of time?
Sir, participants
you
can
get the
unmute yourself.
Pardon?
No, nothing, sir. I'm informing participants can unmute themselves actually, given chance.
Okay.
Oh, okay. So there are no questions. Then I will take perhaps 30 more minutes to introduce the notion of solitons, and then perhaps I will conclude. Any questions? Okay, so now I have considered essentially a single dynamical system, an oscillator under forcing or a map and so on. But you may ask the question, what happens if you consider many such oscillators and they get coupled, connected in different possible ways? So you can form many such connections. For example, you can consider the dynamics of neurons, of the brain. You know, the dynamics of neuron basically is described by the so-called Hodgkin-Huxley equations for propagation of electrical signals. It's a system of 5 coupled nonlinear partial differential equations. But a simple reduction of that in the form of Fitzhugh-Nagumo equation. It's a third order, a second order ordinary differential equation coupled to a first order ordinary differential equation. Effectively, a system of 3 coupled first order differential equations. So if you want to study the structure of the entire brain, the brain consists of billions of neurons. So how these neurons are interconnected and what is the kind of coupling you can think of. So it's extremely complicated network structure that you have to think of. So the study of networks then becomes very crucial to understand the dynamics of the brain as such. So like that, when you want to consider physical and biological systems or engineering systems, many systems, electrical circuits. So I will point out towards the end an interesting circuit, the Murali Lakshmanan Shua circuit, just an LCR, forced LCR circuit with a one nonlinear element. That can show all this behavior of bifurcations, chaos, period doubling bifurcations, and other kinds of bifurcations and so on. So when you couple these equations, what kind of dynamics you can do? So one can consider, for example, linear oscillators under linear coupling. But one knows when you consider such linear oscillators with linear coupling, you can make a linear decomposition, linear transformations to what is known as normal mode decomposition. When you make a normal mode decomposition, normal modes are nothing but basically the standard harmonic oscillators, and they get decoupled. So as a consequence, when you give an initial energy distribution, and in course of time, wait for sufficiently long time, statistical average, then no energy sharing will take place. Energies will remain in the individual normal modes. But what happens if you consider coupling, nonlinear coupling, or introduce nonlinear forces into the dynamics? Simplest situation. And this is what is the famous Fermi-Pasta-Ulam experiments, Fermi-Pasta-Ulam phenomena, and so on. Essentially considering the energy transportation in an unharmonic lattice, nonlinear oscillator plus linear or other couplings. Then you can introduce the notion of damping, forcing, delay, and so on and so forth. So system dynamics becomes more and more complicated. So this is what Enrico Fermi, the very famous physicist who was involved with this nuclear chain reaction between the prior to the, during the Second World War and so on, the computer scientist John Pasta and mathematician Stanley Ulam, who are working at Los Alamos National Laboratory after and during the World War and after the World War. The systems that were developed, computer systems that were developed by Jan von Neumann were become available for university research on scientific problems and so on. Fermi wanted to understand the working of a computer. So he suggested a problem for these this computer scientists and mathematicians who are his colleagues. Essentially, this particular problem. You have a system of mass points, particles. There could be atoms, molecules, etc. in a lattice, one-dimensional lattice. So n oscillators, they are coupled, nearest neighbor coupling under appropriate force. So consider n such coupled oscillator in one dimension, and write down its equation of motion, Newton's equation of motion, the rate of change of momentum, and consider that displacements. Ith particle, the corresponding displacement yi. So the rate of change of momentum, md square yi by dt square, the left hand side. Right hand side is the force between the nearest neighbors. I plus 1, ith particle with I plus 1, and ith particle with I minus 1. So you give the form of the force, then you have the complete equation of motion for the n particle. I fix the 0th particle, the nth particle at the boundaries. So you have a boundary value problem and subject to initial conditions. So you try to give appropriate force. For example, if f of y is proportional to y, it's a linear differential equation because yi plus 1 minus yi minus yi minus yi plus 1, which means yi plus 1 minus 2yi plus yi minus 1, md square yi by dt square. That equation you can make you can go to a normal mode decomposition. From yi's you can go to aj's with these Fourier coefficients. So you can write this linear transformation and find this coupled equation becomes this just uncoupled equation for this new coefficients aj's, which are the normal modes, aj double dot plus omega j square, aj equals 0, where omega j square are just this external constant frequency and some numbers. So that if initially energy is given to this lattice, it can be decomposed independently as the energy of this n normal modes. So no energy distribution occurs in this linear lattice under linear forcing. But then if you introduce a nonlinear forcing, F is also proportional to y square. That means yi plus 1 minus yi whole square. Similarly, yi minus yi plus 1 whole square, or cubic forcing, or broken nonlinearity, which is again linear forcing. Then in such a situation, Fermi asked them to see what happens to the energy distribution. Initial energy distribution is given. How, as time develops, the energy gets distributed among these various oscillators, coupled oscillators. Again, this problem cannot be solved analytically. You have to go only to numerical calculation. So the computer was available at Los Alamos Laboratory, Maniac 1, and these people wrote programs and analyzed this. But unfortunately, by the time results were coming, Fermi was afflicted with cancer and he was in sick bed, and these people didn't want to disturb him. And they have written a report, but Fermi was not in a position to see the read the report. So that report, by the time results were confirmed, Fermi died. These people didn't want to publish this result without the approval, explicit approval of Fermi. So that report remained as a report, internal report of Los Alamos National Laboratory. And that report is LA 1540 or something like that. And this is the report. And this report says that the gist of this report is that a one-dimensional system of particles with nearest neighbor interactions is analyzed, etc., for different kinds of non-linearity. The last line is the most important one. The results show very little, if any, tendency toward equipartition of energy in the degrees of freedom. That means energy does not get distributed equally among this n-particle system in spite of this nonlinear force that is incorporated into the system. Which means when you introduce nonlinear force and use the same normal mode decomposition, it becomes the normal modes get coupled. So you get a system of coupled nonlinear differential equations. And what happens to the corresponding energies of the normal modes? Statistical mechanics says, the basic principle says, when such coupling arises, there should be mixing and wait for sufficiently long time. Energy should get equally distributed among all the modes and equipartition should occur. That is what the basis of statistical mechanics, and which is very important to consider many particle system, condensed matter system. But to the great surprise of Fermi, Pasta and Ulam, this was the result that they obtained. So what I have shown here is the results of Fermi, Pasta, Ulam recurrence phenomena. I have plotted the energies of the first few modes, and they have chosen the oscillators n equal to 32, 64, 128, etc. for certain reasons. So take any of these values and plot the energies. First mode, number 1, second mode, third mode, etc. You start with an initial energy distribution. Most of the energy is given to the first mode, and second and third modes, etc. They receive very little energy. You allow the system to evolve with quadratic forcing or cubic forcing or broken nonlinear forcing. Then they integrate numerically and you follow the system numerically. You do find energy gets redistributed. So more energy, second mode gets, third mode gets, fourth mode gets, etc. So at some point of time, this some normalized time units, they get equally distributed. Then if you wait for sufficiently long time, so for example, to 160 time units in certain normalized coordinates, then you find the first system, first mode gets almost the entire energy back at that time, and all the other modes lose most of their energy. So that means the initial state recurs, and this recurrence occurs again and again when you keep integrating. Again, after this 160 odd time periods, the energy keeps on recurring. So no equipartition occurs. This was a great shock for physicists, mathematicians, and so on, who are all familiar with statistical mechanics and so on. Though this report remained as an internal report, the news came out, and physicists and mathematicians started knowing the results and so on. Different people started approaching this problem in different ways in the late 1950s and 60s and so on. One such approach was taken up by the mathematician Martin Kruskal and Norman Zabriskie at Princeton Plasma Physics Laboratory. So you have essentially this particular system of differential equations, coupled differential equations, with this nonlinear force y plus alpha y square, for example. Now, n is very large, 32, 68, 4, 128, and so on. So you can go to the continuum limit, asymptotic limit. So this is the famous asymptotic analysis one performs for discrete differential equations, coupled differential equations. So that the lattice parameter distance between the equilibrium displacements of the nearest neighbors approaches 0, and n approaches very large. So that yn of t, the discrete value, n becomes is nothing but at the nth point, nothing but if you start from the left end, it's n into a, the spatial position, n into a is the interparticle distance in time. So when n goes very large, when n takes very large and a approaches 0, you can take this as a continuous value, continuous variable x. So y as a function of x and t. Similarly, yn plus or minus 1, you can expand as a Taylor series in the small parameter a, so that y n plus 1 t becomes y of plus or minus a x, a into dy by dx, a square by 2 factorial d square I by dx square, etc., etc. Then substitute into this equation with these variables and so on. Then what do you get? When there is no nonlinearity parameter in the continuum limit, you get essentially a wave equation, which is a linear wave equation. And linear wave equation, 1 c square c is a parameter in terms of this various parameter system, and y is the displacement, vertical displacement, and t and x are independent variables. And you know what are the corresponding linear waves. If you have a linear partial differential equation like this, you know the system admits linear progressive waves, single progressive wave. Take the combination of two nearby wave number progressive waves. You have beats, the phenomena of beats. You take n such waves, 100 waves, 1000 waves, etc. You make linear superposition. Then you find that these waves get localized. A wave packet is formed. So the envelope of which is localized around the center, and the amplitude fastly decreasing to 0 as you move away from the center. So wave group, a group of wave packet becomes possible, in which you have very large number of waves combined in a linear way, linear superposition. And you can integrate the equation by using the linear Fourier transform method in a 3-step process. From the initial condition, you make a Fourier transform, you get the Fourier coefficients at time t0, and you allow the system to evolve according to the linear wave equation. These Fourier coefficients evolve in a trivial way, first order linear differential equation. You can integrate, you can find the Fourier coefficients in an arbitrary time t. You make an inverse Fourier transform, you get this localized Fourier transform as the solution. But then in this Fourier transform solution, individual waves move with their own phase velocity, whereas group waves move with their own group velocity. They are equal only in the dispersionless case. In the other cases, dispersion dominates. As a consequence, group velocity and phase velocity are different. The group of waves, as they progress, they lose their individual nature. The waves get dispersed and the wave dies down. So this is the phenomenon of linear dispersive waves. But if you introduce nonlinear phenomena, the parameter alpha, for example, from that next order corrections, which I pointed out earlier, if you introduce the next order correction, if you introduce these terms, up to this term, for example, second order correction terms, if you introduce that, then you get a partial differential equation, d square additional term, d square y by dx square, plus 2 alpha a dy by dx. But this term, one knows, admits shocks. But in the actual nonlinear lattice, there is no phenomenon of shocks. So Zabriskie and Kruskal went on to introduce the next order, fourth order terms. Third order doesn't contribute, you can check. Introduce the appropriate fourth order term, you get this equation. And you can go to an appropriate new coordinates, going to a moving frame and making a change of variable u equal to 1 over a dy by dx, you end up with this partial differential equation for propagation of waves in one direction, unidirectional wave propagation. Du by dt plus 6u du by dx plus d cube u by dx cube equal to 0. Now, what kind of differential equation is this? You drop down this middle term, it's du by dt, d plus d cube u by dx cube equal to 0. You can check that this is a third order linear partial differential equation with the dispersion relation omega equal to minus k cube. So the phase velocity is omega by k and the group velocity is d omega by dk. So they are never equal to each other. So when you form a wave packet by Fourier transform, the waves will spread. But consider this term, add this term, this is a nonlinear term because linear superposition principle fails. U into du by dx. The dependent variable and its derivatives occur. So total degree is 2. So this is a nonlinear partial differential equation. And this partial differential equation is the famous Korteweg-de Vries partial differential equation, which was deduced by the Dutch physicists Korteweg and de Vries in the year 1895, published in the Philosophical Magazine, to represent a phenomena, a wave phenomena which was observed by one Victorian naval architect called John Scott Russell. This Russell was working for East India Company. His task was to design the hulls of ships so that this company can design nice ships and they can make long voyages to India and Far East and other countries. In the 1800s. So in the year 1834, he was making observations and doing experiments and designing these hulls. During this process, he was observing a boat being drawn in the canal connecting the cities of Glasgow and Edinburgh in Scotland. He was traveling on a horseback on one of the banks of the river. In those days, transportation was in the rivers was by boat, which is being drawn by a pair of horses. So when John Scott Russell was riding on a horseback, he observed suddenly the boat stopped, but not so the mass of water. And he went on to make this delightful scientific observation and publish his observation and further experiments he had done by going to the laboratory and carrying out experiments similar to that. In the year 1844, he observed this phenomena in 1834 August, and he ultimately published his results. It took 10 years in 1944 in the British Science Association reports. This delightful description, I read this. I believe I shall best introduce the phenomena by describing the circumstances of my own first acquaintance with it. What he had observed. I was observing the motion of a boat which was rapidly drawn along a narrow canal by a pair of horses. When the boat suddenly stopped, not so the mass of water in the channel which it had put in motion. It accumulated round the prow of the vessel in a state of violent agitation. Then suddenly leaving the boat behind, the wave rolled forward with great velocity, assuming the form of a large solitary elevation. Solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the canal, apparently without change of form or diminution of speed. I followed it on a horseback and overtook it, still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure, some 30 feet long and foot to foot and a half in height. Its height gradually diminished after a chase of 1 or 2 miles. I lost it in the windings. And this phenomena in a shallow channel connecting the cities of Edinburgh and Glasgow, John Scott Russell made this observation. And John Scott Russell had tried to, had shown on further experiments, he created a long horizontal water column in his lab and dropped waters at one end, dropped weights at one end and created such wave. He measured the velocity and the amplitude of the waves, etc. He obtained a qualitative formula connecting the velocity and amplitude, etc. But the mathematicians and physicists at that time refused to believe what Scott Russell had observed. They said, you cannot have a solitary wave. It's only half of a sine or cosine wave, etc. John Scott Russell died as a dejected person and so on. Not until Kattankulathur and de Vries in the year 1895, starting from basic principles of hydrodynamics, fluid dynamics, starting from the underlying Euler's equation, taking into account viscosity and the heights and the lengths of the wave, the height of water, etc., etc. They introduced 2 small parameters, etc. Through a series of asymptotic analysis, they ultimately ended up with this wave equation. And they also pointed out that this equation admits wave-like solution in terms of CN type sinusoidal wave function. And the limiting form in the beginning, I said, CN function takes the form secant h when the modulus parameter takes the value 1. And it's possible in this case also modulus going to 1, in which case the KdV equation admits a wave solution of the form u of xt is c by 2 secant h square, hyperbolic secant h square. The root of c x minus ct by 2. Observe this form, the standard forms of wave phenomena, sine kx minus omega t, cos kx minus omega t, their Fourier transforms and so on. But here is a wave whose form is secant h square. And interestingly, the velocity parameter c also occurs outside as initial amplitude. The larger the wave, the larger the velocity, and vice versa. So many interesting phenomena occurs. Initial condition dependence of the solution, because larger the wave, the larger the velocity. And new kinds of functions start occurring as wave solutions. If you look at the form of the wave, so this is the form, highly localized around the origin. And if you move away from the origin quickly, exponentially, it falls off to 0. So this is the solitary wave John Scott Russell observed. And it propagates without change of form or diminution of speed. Solitary wave, isolated wave. So that's a new structure that has been. But what has this phenomena to do with the Fermi-Pascal original experiment? Well, this was the question asked by Zabriskie and Kruskal. And they thought the solitary waves had something to do, which was deduced by Kattankulathur and de Vries to describe the John Scott Russell phenomena, should have something to do with the Fermi-Pascal experiments. So at that time, there was no method to solve this Kattankulathur, de Vries or any other such nonlinear partial differential equation. So they went on to numerically integrate using a finite difference scheme, in both discretizing both spatial and temporal coordinates in this particular form, starting from appropriate initial conditions. This is Martin Kruskal, who later became a close associate of our group. He visited our department, our Center for Nonlinear Dynamics several times in the 1990s and early 2000, but he is no more. Martin Kruskal and Norman Zabriskie, they analyzed this problem. So this is what their original picture shows. They started with an initial condition with a periodic boundary condition. So in some units, it has the spatial dimension 0 to 2. So you assume half of a cosine wave. initial condition. You allow the system to evolve according to Kotovic-Debris equation using the finite speed. At finite times, this dotted curve, that is what they obtain. But if you wait for sufficiently long time, you obtain a series of peaks, and they deduce about 10 such peaks. All of that secant h square form, Kotovic-Debris solitary wave form. And you know that, as I have pointed out in the previous slide, that the larger the wave, the larger the velocity. So, if you follow the results of Kruskal and Zabisky, it's obvious that these waves are propagating to the right, unidirectional wave propagation. So, you have a larger wave, you are following smaller waves, but there are also smaller waves, smaller amplitude waves, again secant h form. So this larger wave will travel with higher velocity. Soon it will catch up with the smaller one. It will interact. But to their great surprise, they found these waves interact but come out without change of form or diminution of speed. So two waves, solitary waves, unidirectional propagation. You start from an initial condition, the x-axis, the amplitude, the time axis. So initial state, then the larger wave travels with higher velocity. They interact. After interaction, to their great surprise, these two waves emerge without change of form or diminution of speed, except for a phase shift, like a billiard ball-like collision. So solitary waves, they named as solitons. You have protons, particles, protons, photons, and things like that. They're stable structures. Similarly, solitary waves, even under collision, they retain their shape and form. And if it has such property, they call as solitons. And that is the birth of notion of solitons and new physics, new mathematics, leading to integrable nonlinear dynamical systems. Solitons are nothing but solitary wave which retains shape and speed under collision except for a phase shift. But in Kruskal and his co-workers, they not only stopped with this numerical analysis, they went on to deduce a new mathematical techniques akin to the linear Fourier transform techniques, which is applicable to linear dispersive waves. They deduced what is known as inverse scattering transform method to completely solve the initial value Cauchy initial value problem associated with this third order nonlinear partial differential equation, namely the Kotovic-Debris equation. You start from an initial value u of x0, which is an obvious physically admissible one is u of x0 pulse off sufficiently fast as x goes to plus or minus infinity, one-dimensional spatial extent. So what they did was they associated this Kotovic-Debris equation with two linear spectral problems. So consider a linear eigenvalue problem, the Schrodinger spectral problem, second order, minus d square by dx square psi plus u of xt psi equal to some lambda psi, where lambda is an arbitrary constant, where u of xt is the unknown function of the Kotovic-Debris equation. The wave function psi evolves, and as far as this spectral problem is concerned, the time occurs just as a parameter. It doesn't do anything here. Just the derivative is only with respect to x. So you can ask the question, how psi evolves in time? So this is a linear eigenvalue problem. If psi is chosen such that d psi by dt, the partial derivative, d psi by dt equal to another linear differential operator, this time as third order linear partial differential operator, b psi, where b is minus 4 dq by dx cube plus 3 ud by dx plus dxu, that is 3 into u d psi by dx plus ux psi plus u d psi by dx. That is what you will get here. So this is again a linear partial differential equation. Now take the compatibility of these two. Take the time derivative of this equation, spatial derivative of this equation, equate psi of xt equal to psi of tx. Then you get LT, this operator equation, LT equal to BL operating on psi, because L and B are operators. They have to operate on something for me to be meaningful, and they operate on psi. So the resultant LT commutator BL, which is BL minus LB, is nothing but the KdB equation. So Kotovac-de-Vries equation, you can check this. Kotovac-de-Vries equation and a third order nonlinear partial differential equation can be associated with these two linear partial differential equations. Linear partial differential equation, you know a lot of information, you can make use of this. In particular, this eigenvalue problem, you can treat this as a potential. U has the property U vanishes sufficiently fast at plus or minus infinity. So that is a spectral problem. Linear spectral problem. You know the spectral properties of this problem. It has got the spectral data, discrete bound states and continuum states characterized by reflection coefficients and so on. So scattering data can be identified, and given information is initial data U of x0. From U of x0 you can find the scattering data at t equal to 0. Now, just as in the case of Fourier transform technique, you ask the question how this scattering data evolve in time. For that, you make use of this part of the equation, time evolution. But here you find psi t equal to b psi equal to minus 4 d cube psi by dx cube plus 3 u into this psi. But u goes to 0 sufficiently fast at x equal to plus or minus infinity. Now these spectral data are properties at infinity. So you have effectively a linear, trivial linear partial differential equation psi t equal to minus 4 cube d psi by dx cube. As a consequence, spectral data also evolves as a linear ordinary differential equation, first order. You can solve them trivially. So you can find the Fourier, the scattering coefficients at an arbitrary future instant of time. Now you can ask the question, if you have this scattering data at future instant of time, how to invert and get the potential? And that can be deduced by solving a series of, solving a system of linear Volterra type singular integral equation, linear integral equation. Again, a three-step process. Starting from initial value, you carry out a direct scattering, and scattering data at t equal to 0, time evolution, and that is trivial. You get scattering data. But now you have to solve this linear spectral problem and linear integral equation. This information, because all these things were available during 1950s by Russian mathematician Gelfand, Levitan, Marchenko in connection with nuclear potential scattering problem. So making use of that, you can find the potential exactly analytically, and the consequence of which is that you have the single solitary wave, which was obtained by Kotovac-de-Vries from simple reducing the KdB as an ordinary differential equation. But you can get more general soliton, two soliton solution in terms of two wave parameters, which exactly represents this numerical analysis. You plot that function, you will get exactly this picture. You can get 3 soliton, you can get n soliton, and you can solve the full Cauchy initial value problem, which will be, the solution will be n solitons asymptotically with different velocities in the background of oscillatory dispersive wave, which anyway will die down. And as a consequence, you have completely solved the initial value problem of the linear partial differential equation. And so you have an infinite dimensional, completely integrable Hamiltonian dynamical system, because you can identify a Hamiltonian structure for this Kotovac-de-Vries equation, and you can point out that this inverse scattering transform method is a canonical transformation to action angle variables. And so it's an infinite dimensional integrable Hamiltonian dynamical system. So that leads to the new development of integrable dynamical systems, infinite dimensional, and so on. For example, tsunamis, the 2004 tsunami, that you can show as, can be shown to be related to the Kotovac-de-Vries equation, and the tsunami wave can be shown to be related to the Kotovac-de-Vries solitary wave. You know, the tsunami wave progressed as far as away from off Sumatra, started and traveled as far as away to Kenya and Somalia and so on, and then not only the India coast, but also Somalia coast, etc. And in history, there are so many such tsunamis which are formed, and you can identify it with KDV and similar solitary waves and so on. But it's not only that, there are many such systems. For example, magnetic solitrons, Heisenberg ferromagnetic chain, for spins I have shown in as far as 1977. It's a completely integrable solitronic magnetic solitrons and optical fibers, light and intense laser light propagation, nonlinear Schrodinger equation, Long-Josephson junction, Sine-Gordon equation, which also occurs in differential geometry, even discrete systems, Toda lattice equation, etc. All these systems are associated with different linear eigenvalue problems and their time evolution, and they can be shown to be integrable, infinite dimensional Hamiltonian dynamical system, and the same inverse scattering transform. So like that, there are many such nonlinear partial differential equations in one space, one time dimension, which have been identified, and corresponding to different physical situations. So another possible situation, Manakov model, describing light propagation in photoreflective media and multi-mode fibers and so on, which my group have shown again has possess solitons of different kind. Under collision, their shape changes, but the shape change is in the form of linear fractional transformation, leading to optical logic gates, and which some computer physicists from Princeton University have taken up, and they have pointed out that originally we thought that integrable systems admit only a pure elastic collision, but the paper of Radhakrishnan, Lakshmanan, and Heta gave us a completely surprising result, and through which one can show that how state variables changes leading to design of optical logic gates. And recent times we have pointed out this kind of equations exhibit even novel structures, but I do not have time to go into all those details. I will skip all this. And new kinds of solutions, breathers and rogue base in our group and other groups, a lot of people have studied. So the study of solitary wave solitrons continues to be excite people, and in many directions, geometric, group theoretic, singularity, structure, etc. have been investigated, and new developments, new procedures, methods have been developed. There exist finite dimensional systems which exhibits many such properties. Unfortunately, I do not have time to go into all those details. New equations, new structures, etc. one does get while approaching, for example, Matthews Lakshmanan nonlinear oscillator, which has got very nice properties. Nonlinear, it's more complicated. In recent times, even with cubic and harmonic oscillator, position-dependent nonlinearity, leading to non-standard type Lagrangian Hamiltonians, new class of integrable systems can emerge. So I will take 5 more minutes. I have already taken a lot of time. Just to complete, you can ask the question, for example, if you include damping, forcing, etc. For example, if you add 2 coupled oscillators with appropriate coupling, what can happen? Very surprisingly, you can plot, again, numerically only you can study, you can plot x1 versus x2 versus t time trajectories. In general, they do not follow each other, but under appropriate coupling, they can follow each other. So if you plot x2 versus x1, there is a nice 45-degree diagonal line, which means it's coupled when they are exhibiting periodic motion. But very surprisingly, I pointed out these oscillators exhibit chaotic motion, highly sensitive to initial conditions. What happens when you couple such systems? Even when you take 2 uncoupled systems, they never correlate. X1 versus X2 is very complicated structure. But when you introduce coupling, as you increase the coupling strength appropriately, you see some order in X1 versus X2. And very surprisingly, at a very critical coupling and beyond, you can have complete synchronization of the motions, X1 and X2, both the oscillators. And then there are phases can correlate, or there could be functional correlations, generalized synchronization. So many kinds of synchronization have been identified in recent times. Complete synchronization, phase synchronization, generalized synchronization, lag, anticipatory, inverse synchronization, and so on. Many such systems. When you consider coupled systems, you can consider many such oscillators. For example, 100 oscillators you can couple. Black lines means uncoupled. The red lines partially coupled. Yellow line means complete coupling. So under appropriate coupling, this is the number of oscillators, and this is a coupling strength, etc. You can find coupling. So many such developments are taking place. You have many complex phenomena, hurricane, turbulence, stellar cloud, etc. Or patterns, different kinds of patterns you can identify in nature. So chemical patterns, nature, ferns, in zebra, etc. So if you introduce appropriate diffusion into the problem, then you can see one set of patterns. So I pointed out neurons, couple neurons. When you consider Hawking-Huxley, Fitts-Nagumo equation, you can even consider phase coupling and so on. So again, you can ask what are the collective motion that can exhibit in this kind of coupled oscillators. Circuits, LCR circuit with forcing a nonlinear element, a piecewise nonlinear element. So this is called Morley, Lakshmanan, Chua, Leon Chua. So we have studied this system. This exhibits very nice bifurcation structure, period doubling bifurcation structure, etc. So you can consider a multitude of the coupled such MLC oscillators. So many such oscillators, so you have period doubling bifurcations and other, just like the Duckling oscillator or the logistic map, etc. So there are many other systems, spin systems. Maybe I will skip all this. So I will not go into the details of these systems. Land-Oblip equations, spin currents passing through nanostructures of this magnetic structure. So they again exhibit bifurcations and period doubling bifurcation, nice chaos and so on. If you ask the question, what happens inside this chaotic regime, many interesting bifurcations and chaos occurs. The study of them still people are trying to pursue. So anybody can take any of these systems and try to explore what is the intricate structure inside this chaotic bands. Again, synchronization can occur. Chaos computing is also upcoming idea, just like soliton computing, optical computing, chaos computing is also emerging area. And then collective dynamic states in coupled systems. Unfortunately, I do not have time to go into these studies, but different kinds of couplings, local coupling, global coupling, non-local coupling, that means few oscillators are only collected, etc. What kind of ultimate states can identify? One can identify completely incoherent random states, coherent, completely smooth profile, chimera states in a single group of randomly distributed oscillators, remaining oscillators in an incoherent state, and so on. So many kinds of such collective states have been identified in recent times. So this is a cohera, this is a chimera, and a single entity having different kinds of lion's face, goat's body, snake's tail, etc. Or you go to Dharasuram temple, you see Yali. Yali is a structure which is again similar to this chimera of Greek structure, etc. Such structures occur when you consider collective dynamical states of many systems. So I will not go into the details. So we have given details, statistical characterizations of such structures in terms of what is known as strength of incoherence and discontinuity measures and so on. So all these studies are being utilized by many people in recent times. I would have loved to describe these structures in more detail, but my time has run out. I've already taken too much time. So to conclude then, nonlinear dynamics continues to be a challenging and fascinating area of research. In physics, mathematics, basically mathematics, physics, chemistry, biology, engineering, and even economics, social science, and so on. Many novel problems in physics and associated mathematics remain still unexplored. For example, I talked about few nonlinear partial differential equations, few ordinary differential equations. What about other kinds of systems? We changed. I initially started saying that each class of each nonlinear system is a class by itself. That continues to remain the same, I think. One can look for continued progress. So some references, my own book, Lakshmanan Nonlinear Dynamics, Interpretive Chaos. Many of these points I have discussed. You can get these structures. Chaos in nonlinear oscillator controlling and synchronizing Murali and myself. Recent time dynamics of nonlinear time delay systems, Springer lab modeling, and encyclopedia of nonlinear science, complexity system science, and many other recent references. So I think this is a point where I will stop my lecture, and if you have any questions, comments, I will be happy to answer. Thank you very much for your attention.
Thank you, sir.
Thank you, sir.
Thank you, sir. This is Bapuji. It's like a one semester syllabus, sir. It's like a version. We have to take 6 months. I can understand what you have done.
Sir, thank you for presenting in a. Thank you for presentation. You have given all the history.
Can I stop share at this point?
Yes, sir.
Yeah,
Yes, sir. Please.
You can start, sir.
Please.
Yeah. Sorry, I've discussed many things, but I think these are the preliminary.
No, sir. A lot of things are there, sir. You have to do a lot.
Sir, you are given a brief introduction. You are given a good introduction, including all historical backgrounds, whatever research is going on in nonlinear dynamics, chaos theory, and its application, whatever be the application, other field, everything you have given in a detailed manner. And I don't know whether anybody could give better than this. Even if anybody can give in online, that is also you have to mention. If it is through in-person presentation, that is a different issue. But you have done a presentation through online, and that too in an amazing manner with all the possible visuals, examples, and also the historical background. It's a great, really a wonderful lecture. We are very proud to have your lecture, sir. We are happy to listen to you. And
just at this point of time, you can go to Bharathidasan University BEH website. I have given a series of 7 lectures only recently. Still, it's going on. This somewhat expanded aspect of what I have tried to talk today. So if anybody, any student is interested, he can also go to that website and try to get, can still register, I think.
Okay, sir.
Get, some idea of in more detail.
Okay, okay. Thank you, sir. Thank you. Those textbooks you have mentioned, is it easy for the beginners to follow, sir? Those who are working in other department?
Yeah, I think many universities and colleges making use of this book to give an introduction to nonlinear dynamics. At least few parts of it one can make use of. Okay, sir. Sure, sure. We'll follow it, sir. Yeah. And is it available online or is it available online? Yeah. So you have to start from linear differential equations and then progress to nonlinear differential equations and equations. Okay. But I think group theory and differential geometric structure, etc., they're all very useful in this field, complex analysis. So, so the more you know, the more you make use of your mathematics, the better understanding one can get. So mathematicians are the best persons to make progress in this line. In fact, many of the top contributors in this field are from mathematics. So interested young people should pursue these areas. So originally P.L. Bhatnagar, who wrote the first book, I asked Martin Kruskal, what book you have followed? He said, I didn't follow anything. I gave my own lectures, but one book I used to make use of for my own lectures is by a book by P.L. Bhatnagar. So that was published in India, the first book, and it deals with Quadratic-Debris equation in some detail. So that I understood from Professor Pullepu Prasad, P.L. Bhatnagar was his supervisor. P.L. Bhatnagar for Pullepu Prasad and Professor P.L. Sachdev from IISc Maths Department. So people can look into P.L. Bhatnagar's book to get some idea of nonlinear shading of Kotabek-Davis equation. But in my book also, I have given a detailed derivation of Kotabek-Davis equation for as followed by Kotabek and Davis.
Thank you for your information, sir. And in your presentation, you have shown most of the profiles of the nonlinear systems. Is the profiles actually drawn and generated by you, or you are used any solver for getting those profiles?
All these figures were obtained by my people from my own group.
Okay, okay. Your students.
I have not used. I mean, they generally do not make use of any particular available codes. They write their own codes. Okay? So very rarely they make use of outside codes. So by that way, they learn a lot about this nonlinear system. Of course, there are many codes available, but I would suggest strongly people try to write their own programs and develop techniques to reproduce already known results, and then they can go to new systems. By that way, they can learn quite a bit.
Most of the naturally occurring phenomena are nonlinear in nature. They can be represented by either a nonlinear ODE or nonlinear PDE. I think the participants have attended your lecture and it will be a starting point for them to learn about nonlinear dynamics so that they can have a better understanding of naturally occurring phenomena. That is my assumption, sir.
Okay.
Any other questions from the audience?
Professor, good afternoon, Professor. I am Dr. Subramanian from SRM IST Ramapuram campus. Really, I am very fortunate to hear your lecture. I have only one question. As the solitons are used to send the optical signal in the fiber, like can I know that the applications of the dromayon, lump, a breather, etc., sir? Any other practical application of the dromayon so far, like solitons?
Dromayons. So the nonlinear partial differential soliton system I talked about are essentially one spatial, one time dimension. So you can ask whether you have such structures when you go to higher dimensions, because most of the natural systems are 2 dimensions, spatially 2 dimensional, 3 dimensional, so on. You can go to 2 dimensional systems, then again ask whether you have similar phenomena, similar methods, techniques available. So there are a few systems, Davies-Stewardson equation, which is a generalization of the nonlinear Schrodinger equation. Nonlinear Schrodinger. Or the Kramstorff-Petiashvili equation, which is a 2-dimensional generalization of Kotabek-Davis equation. Some of these equations do admit exponentially localized structures, and they have their own collision properties. Not exactly like solitons; they can undergo under collision different kinds of scattering phenomena and so on. They're not completely understood, but they have some interesting collision properties. But the point is, the kind of equations which admit these dromayons and so on, they're slightly artificial. They are not direct generalizations of this KdV equation or nonlinear Schrodinger equation or Sine-Gordon equation or Heisenberg's equation. So they have limited usage, but these dromayons, etc., they are again localized structures possessed by a few of these 2 spatial, 1 time dimensional nonlinear partial differential equations. Then if you ask the question whether similar structures occur in 3 spatial and 1 time dimension, which is the most general physical dimension we can think of. Hardly any interesting nonlinear partial differential equation seems to admit such a stable localized structure. So developments in mathematics and the corresponding connections with physical systems can only show in future the use of these kind of structures, or identification of what kind of basic structures like solitons in one space, one time dimension exist in higher spatial dimension structures. The mathematics, the inverse Fourier transform technique, they have to be generalized to study of this linear spectral problem in the complex eigenvalue plane in two spatial dimensions. So the mathematics becomes more and more complicated, but that is very interesting and challenging to study in higher spatial dimensions. So a lot of scope there, but as of now, there is not many fascinating phenomena which are identified in 2+1 dimension, contrary to 1+1 dimension.
Okay. Thank you, sir. Thank you.
Okay. Any other question?
Hello. Hello. Hello.
சொல்லுங்க.
Okay. How to develop nonlinear ODE from real life data?
How to
develop nonlinear ODE from real life data?
No, all the
Hello.
He got the question and is answering.
Hello.
He got the question, Bala.
சொல்லுங்க sir.
He got the question and he is answering, I think. We are not able to hear.
Okay.
Not audible, sir. Ashwin sir.
Lakshmanan sir.
Yeah.
Not audible, sir.
Are
Hello.
you able to...
Yes, sir. Yes.
Yeah. The dynamical systems I have discussed, the ordinary differential equation, for example, the Duckling Oscillator, the MLC oscillator, or any of the system I have discussed, or only from real life dynamical situations.
Data.
Sir,
Hello.
Using data, how you will form the
Hello.
No.
Hello.
The data you take from initial.
Hello. Okay. Sir, how to develop nonlinear ODE in real life data? Like this pandemic situation, COVID-19 data already published right now. Then how to develop nonlinear ODE? That's my question.
Yeah, we have also developed a model for COVID-19. So it's available in the archive. We have put it about a month back. So it is under refereeing in a journal and so on. So you can form models from the available information. So from the data itself, you can try to identify parameters and the appropriate model. So there are ways and means of doing that. But then from the phenomena, so when you have a large number of data, you start from an appropriate model based on the physical situations for like the COVID-19. You have SIR model, SCIR model, etc. And deduce appropriate results and then try to map it on to the actual real life data available. For example, the COVID data that is available on the website, you try to map whether the model you have put forth tries to reproduce the available data exactly. And from that, you try to project what will happen, when will the maximum infected persons, the number will arise, or what will be the contribution from the people's contribution, etc. So you can try to give some information to the concerned people from the model you have started working on. Okay. So from the data, large number of data, you can try to work out a model, simplest model that one can. That is one kind of approach from model-based result-based model, but starting from a model, you try to develop the results, which on a large extent tries to mimic the phenomena. Then after you deduce the result, you try to bring in the actual data that is available, compare, and you can fix the necessary parameters in the model. Then you try to go to the future development and make a prediction. So that is also possible. So that's what people do for COVID-19 and so on.
Yes, sir. Thank you, sir. Sir, when exit bifurcation from tau in delayed differential equation? Is there any critical points are there, sir, already?
Yeah,
bifurcation.
In time delay systems also large kinds of bifurcations do occur as a function of delay parameter and other system parameters.
Is there any fixed values are there, sir?
No, it's not
bifurcation.
Yeah, bifurcations occurs. So in all these nonlinear dynamical systems, bifurcation occurs as you change the system parameter, control parameter continuously. So from a fixed state, you can enter a periodic state, and then period doubling on possibility, and then quasi-periodic or very kinds of sophisticated bifurcations. So as you change the parameter continuously, all kinds of bifurcations can occur. In time delay systems, the bifurcation structures will be even more complicated. So you can look into the book, myself and Senthil Kumar, many details about this.
Sir, another one question, sir. Which situation we frame integral boundary condition, sir? Already, which situation we frame integral boundary condition? When do you apply integral boundary condition in nonlinear ODE?
Now, the nonlinear ODEs, you apply appropriate boundary conditions depending on the physical problems you have in mind. For example, in the case of the one-dimensional lattice and harmonic lattice, I have fixed the boundaries at both the ends. I equal to 0, n equal to 0, I equal to 0, and I equal to capital N. So that means that is an integrable boundary condition in the sense the fixed point, the values of the variable x, y naught and y capital N are always 0. So that is one simple integrable boundary condition. So like that, depending on the physical problem, you can fix the boundary conditions. So most of the physical systems, you will make use of integrable boundary conditions. Variable going to 0 at large values, which is a natural boundary condition. So like that.
Sir, one more doubt, sir.
Yeah.
In perturbation techniques, what is the difference between approximate solution and analytical solution? Some others already set analytical solution. Some others said approximate solution. Which one is correct, sir?
Analytic solution, by analytic solution, I mean the exact solution of the given nonlinear, ordinary, partial, or integral, or differential. That is, the system satisfies the given differential equation exactly. You substitute the given solution in the left-hand side, that is equal to 0, or whatever it is on the right-hand, it satisfies. And if you want most general solution, then you should have enough number of arbitrary constants. If in an nth order ordinary differential equation, there should be n independent arbitrary constants. Okay, whether it's linear.
Sir, suppose if you apply some power series solution in boundary layer, we don't get the general term, sir. Then how to say this one is approximate solution or analytical solution?
No, approximate solution means the solution doesn't satisfy the differential equation exactly. It only satisfies to certain order in one of the parameters in the problem. You treat the solution as is valid to certain order in one of the parameters of the problem. So that's why you develop perturbation methods, perturbation in certain parameters. Okay. So only when you do the analysis up to infinite order and the sum of this infinite series, when you sum up, it should end up in a finite function. So So this never happens. So most of the nonlinear problems, you cannot do infinite series solution. And even there, most of the problems you find even the nonlinearity parameter lambda equals 0 is an essential singular point or points where you cannot really, the range of convergence is extremely small or even 0. So there are a lot of difficulties.
Sir, please suggest one good book in numerical schemes, like Hope Bifurcation and Chaotic Behavior. Is there any good numerical scheme from with which book, sir? Numerical scheme.
Other bifurcation, I strongly suggest you try to develop your own program, your own code. That's so simple. Don't try to follow the available code and all. So I think by that way you can learn a lot. But there are many books where you can find the techniques to write down.
Thank you, sir. Thank you, sir. Thank you so much.
Okay. Any other question from the audience?
No, sir.
Any other question? Okay, if there are no questions, I thank Professor Lakshmanan for sparing his valuable time with us.
Sir, I have one doubt, sir.
Please.
Sir, Lakshmanan sir, good afternoon. I am Dr. Sindamari from Max Department.
Yes, sir.
Sir, you told that number of independent required constant appear means it is a general solution. Can we say exact solution? Exact solution. Suppose approximate or analytical solution, we found.
The general solution
Yes, sir.
will admit, if it's an nth order differential equation, ordinary differential equation, it will admit n arbitrary functions.
Arbitrary functions. Okay.
N independent arbitrary functions. So you substitute such a solution and it will satisfy the given differential equation. But you can choose some of these arbitrary constants to be 0.
Okay.
They cannot be available. So n, instead of n arbitrary constant, you may have n minus 4 arbitrary constants in your solution. That will also satisfy the differential equation, but this is a particular solution.
Okay.
So general solution, particular solution. So you have to distinguish between. But if you have a particular solution, you have to worry about the stability of this solution in a nonlinear.
Sir, in our research work, we are finding approximate analytical solutions, sir. But it will satisfy equation.
Approximate analytic solution, so it has a range of validity. So it is valid only for a small parameters. It's not an exact solution.
Yes, sir.
Still, it could be useful for practical purposes when you do not have an exact solution.
Okay. Okay. Thank you, sir. Thank you for your valuable explanation, sir. Thank you so much.
Any other questions from the audience?
One more, sir. Sir, one more question.
Yeah.
Sir, I am Adityan from Maths Department, sir. Sir.
Please ask your question.
Yes, sir. Sir, actually, you are telling about creating our own code for solving second order differential equation means we are actually at present we are following some second order differential equation or a system of differential equation to solve Runge-Kutta method or Euler method as a methodological solution, sir.
Yes.
Actually, can we solve second order differential equation with our own code means what kind of methods? Finite difference method you are specifying or any other, sir?
Make use of this available Euler method or Runge-Kutta method, start from second order Runge-Kutta, fourth order Runge-Kutta. Sometimes you
even finite difference
have to go beyond fourth order Runge-Kutta or find any other known method whose properties etc. are well understood mathematically. So make use of that kind of
okay, sir.
Methods to write your own codes.
Okay. Any other questions?
Sir, that's what I want, because you are telling your own. Okay, sir.
Adityan, any questions? Any other questions?
No, sir. Thank you. This question only.
Okay. Any other questions from any other audience? Okay, if there are no questions, I thank Professor Lakshmanan for sparing his valuable time with us and delivering a talk on nonlinear dynamics. He threw light on how nonlinear dynamical system works, what are the principles behind it, what are the methodologies behind it. I think the participants would have enjoyed this lecture. I also request the participants to log on Google to Bharathidasan University, and where Sarah has given a series of lecture, and you can also join if you are interested, so that the participants can know better knowledge, they can gain better knowledge about the nonlinear systems. So thank you, sir, for sparing your valuable time and answering all the participants' questions. Thank you, sir. Thank you.
Sir, can you share the PPT with us? Sir?
Yeah.
Yes, sir. Thank you. Because it has lot of information, sir. We can learn from the PPT.
Sir, you can share to Dr. Balamulidharan, sir. Dr. Balamulidharan gave an email ID to you. You can share to him, sir. We will get it from him.
Okay. Thank you very much.
Oh, thank you, sir. Thank you for spending your most valuable time.
Yeah.
Thank you, sir.
Thank you, sir.
Bapuji, can I leave the meet?
Yes, sir.
Okay,
Yes, sir.
sir.
Please,
You can
please.
leave, sir.
Yes.
Thank you.
What about the feedback, Bapuji? All
Posted,
the
sir. Posted, sir.
okay.
Okay, Bapuji. Shall I leave? Shall I wait or leave, Bapuji?
If you have completed feedback, you can leave. Ujay Kumar. Ujay Kumar.
Yes, sir.
If you have completed the feedback,
I have completed, sir.
you can leave.
Okay, sir. Thank you.
Ritesh Kumar.
Unmute, sir. Ritesh, sir. Unmute.
Unmute.
Talk, sir. Speak out.
Yeah, it was a nice
Yeah,
talk,
sir. It's like
but
a
it was very
semester.
long. It is difficult to concentrate for the whole two and a half.
Yeah.
It's like a semester syllabus, sir. Actually, it's not a talk.
Yeah.
We have to sit and learn 6 months, sir. We
But,
cannot. It's very good syllabus.
Actually,
No. You see the difficulty of the speaker. How
Yeah.
much patience he should have for delivering such a wonderful lecture for 2 hours.
Yes, sir. Yes, sir.
yeah, it is good that speakers are really very enthusiastic to speak this much, because it's tiring also. And I was actually wondering that he has 98 slides, and
Yeah. After 50, is actually pushed off.
so I was actually, when it was 40th slide, I was thinking that how long it will take for him to finish, but it's okay. My laptop mobile battery is also gone.
No, at least our faculty members can learn something out of it.
Sir, actually, for the online teaching, I don't know how it will help.
No. Not for online teaching. Suppose doing research in nonlinear dynamics or any other related area.
Yes. That way it will help.
At least doing project with the MSc student.
Yes. So how many are left? Up to 11th, no? How many are left? Such.
Another 4, sir. We go up to 16th.
Okay.
So for faculty and for research scholars, we start from 17th. 17th to 28th.
Okay, sir. Take care of yourself, all of you.
Okay, sir.
Yes,
Bye,
yes.
sir. Take care, sir.
Thank you.
Bye.
Bye.
Sir.
Yes.
Already, sir. I'm closing,
Yes.
sir. Already.
Yeah.
2 o'clock, sir.
Okay, sign out.
Saturated.
Okay. Please sign out.
Can I push off?
Okay. Please end the meeting.
Okay, sir. Radha.
Yes, sir. Yes, sir.
பண்ணலாம்ப்பா.
பண்ணிடலாம் சார், க்ளோஸ் பண்ணிடலாம்.
முடிஞ்சு போயிடுச்சு. தமிழ்வானா ரோட்ல சுத்துறியா? தமிழ்வாணன்
சார் ரெக்கார்டிங் ஸ்டாப் பண்ணுங்க.
Recording பண்ணிட்டானே.
Stop